In today's note, we're going to be looking at dynamic analysis. So we're going to be looking specifically at residuals, which we've talked about in a previous note, and residual plots. So if we recall for what a residual is the difference between a data's actual dependent value and the dependent value predicted by the line of best fit. So we talked about this when we looked at the line of best fit, and the residual is the difference between the actual dependent value and the one that's predicted by the line of best fit. A residual plot is a graphical representation that shows the vertical distance of each residual from the line of best fit as data to a horizontal line. So basically, when you calculate the difference, it's plotting that difference. So it's going to be plus or minus whatever the difference is from the line of best fit. And ideally, if your residual or if your data 100% fit your line of best fit, then you would have a residual plot where all the points are on 0, because there would be no difference from the actual dependent value and the dependent value predicted by the line of best fit. So if we were to look at a residual plot, this is a residual plot here. We have our values, and we have the dependent on the bottom, and the residual difference is on the y-axis or the dependent axis. So each point you can see shows you the value of each point away from the line of best fit. So if you were to have a graph where all the points were on the line of best fit, they would all be lined up across 0 because there would be no difference. We can see outliers similar to those in a scatter plot. An outlier is a point that is far away from the line of best fit that doesn't follow the trend, and the same can be said for a residual. So this point is far away from our line of best fit, or our 0. So in an example, the following table compares a jewelry store weekly diamond ring sales to the minutes of radio advertising purchased for the same week. What we want to do is create a scatter plot and perform a linear regression. Then once we've done that, we want to describe the trend, and is a linear model reasonable in this case? So what we're going to do is we're going to go through and we're going to plot this data into Desmos, similar to what we've done in previous notes, and we are going to create a scatter plot and then create a linear regression. And when we go through and we do that, this is what we should get. So we've plotted our points, and then we've created a linear regression by using the y1 squiggly line mx1 plus b, and we've come up with our r squared value, our r value, and our m and our b value. And let's create our line of best fit. So here's our scatter plot. Now going back to the question, is this a good linear model? So looking at specifically our r value and our r squared value, because our r value is equal to 0.9429 and our r squared is equal to 0.889, we can say that this is a strong positive correlation, and we can say that as advertising increases, ring sales also increases. So and we could say that this linear model is a good fit because, again, of the strong or the high R value. Because it's 0.9, we'd say it's a strong positive correlation. So we'd say the linear model is, or linear regression is reasonable for this. In B, if we want to interpret the residuals for each point, and again, remember this is just x and y, x and y. So here we have 2 points where 20 hours and 7.9 in the thousands sales, and 18 hours and 4.7 in sales. So again, remember that a residual is the difference between the actual cost of the ring or sales and the predicted cost. So these are the actual values. What we need to do is determine the predicted cost. And what we're going to use, if we go back, we are going to use our linear regression, y equals, if we go back, y equals 0.328 x minus 0.30871. So we're just using the m and the b value from Desmos to come up with the actual linear function. And now we're going to find the predicted value. So when we go through to calculate the predicted value for the first one, get y equals 0.328 times x, which is 20, minus 0.30871. Get y equals, should get 6.25489. So this is our predicted value. And now, in order to actually calculate the residual, we have to take the actual value, the 7.9, subtract the predicted value, and we get our residual, which is 1.64511. We're now going to do the same thing for the other point. So again, we're going to take our linear function and substitute the values in for x to determine what our predicted value should be. So 18 minus 0.30871, and we should get a predicted value of 5.59853. To calculate our residual, we need to find the difference. So the actual value is 4.7 this time. Subtract the residual, 5.59853, and we get a residual of negative 0.89853. And that is our residual. So normally what we should see is that normal residual lines have equal number or equal data above and below. Because again, when you're creating a line of best fit, not all points are going to be exactly on the line. Not going to be exactly on the line. So you want to make sure that the line of fit goes through equal number of points and have equal number of points above and below the line. So the next thing we're going to do is construct a residual plot and describe the pattern in it. So when you're using Desmos, the easy way to plot your residual plot is when you create your linear regression. This is not the same data, but the same image would be similar. You would see a spot on your graph that says residuals, E1, and plot. And what you're going to do is you're going to click the plot button and it will plot your residuals. Now you may have to remove the data or unhighlight it in the other cases so that all you're seeing are the residuals and not your line of best fit anymore. But what you should see when you create your residuals for this scatter plot is what you see here. And you can see at the top how we don't have the Y1 values highlighted anymore or the linear regression because we don't want to have those images on our graph right now. We only have our residuals, the E1, being plotted. And as you can see here, with our data, we have an equal number above and below our residual line or the line of 0. So that means that we have a good linear model because we can see the differences between the actual values and the predicted values is very close to 0. Now, when we're looking at that, we may come across outliers. And an outlier is a data or a data point that falls outside the trend or pattern of the rest of the data. It is far from the line of best fit, and it is as well far above or below the horizontal residual line. So we can see here, just a small demonstration, the point out on its own is the outlier. So in example 2, the following table shows the sale price for several used motorcycles of the same model and age. Right, so we see the age in years and the price that it's sold for, and we want to create a scatter plot of sale price versus age and a linear regression, and then discuss the goodness of fit. So you're going to go through and enter this stuff into Desmos again. You would clear all the data or start a new graph and insert a table and go through and enter all of it. And when you're done, what you should come up with is something similar to this. And when you're looking for the goodness of fit, in terms of the linear regression, what you're looking for again is your R squared and your R values. So our R squared value is equal to 0.5835, and our R value is equal to negative 0.7639. So you could argue that it is moderate negative correlation. And you could argue that, or you could say that because of the R squared value, 58% of the variation is due to the independent variable, but that also means that 42% is due to randomness, which is quite a lot, or quite a high percent. But we could still say that it's a moderate negative correlation. There is a relationship between the age and the price. The next thing we want to do is construct a residual plot and identify any outliers, and suggest reasons why these outliers may exist. So if we construct a residual plot by going to the same thing, clicking on the residuals or plot button that you would see down here, we've already clicked on it so it doesn't come up again. We see the residuals plotted. We've unhighlighted the Y1 and the linear regression, just so we don't see those, so we only have our residuals. And we should see that we do have an outlier. We have an outlier down here that we could have picked up as well from looking at our scatter plot, but we can definitely see it with our residuals, and this is our only outlier. So suggest reasons why this outlier may exist. So what it's saying is this point does not fit the trend. So if we go back and we look at that point on our graph here, what we're seeing is that a bike at this age should be selling for higher. So why might this bike not be selling for that much? Maybe it's damaged. So maybe the bike is damaged. Maybe there are a lot of miles or high mileage. Wasn't taken care of properly. There's many different factors that may cause a bike not to sell it for as much. Maybe they didn't care how much they got. Again, there's no right or wrong answer. You're just coming up with reasons for why this point is the way it is, because it's not a wrong data point. It just doesn't seem to fit the trend, so something else must have happened. So what we're going to do is we want to remove the outlier because we know it doesn't fit the trend, and we want to repeat the regression and compare the models. So if I've taken out that outlier, we see that the outlier should be down here at 3 and 2, but it is no longer there. So if we're comparing our two linear models, what we can do is we can go back and look at the R squared and the R value. And what we see here, when we see our R squared is equal to 0.9465, and our R value is 0.9729. So what we can say now, it is a strong negative correlation. So the negative correlation doesn't change, but the fact now is that it's a strong correlation. It's very close to 1. And we can also say that 94% variation is due to the independent variable, and only 6% is due to randomness. So this is much better in terms of an R squared value, because the variation is highly dependent or very likely due to the independent variable changing, and very small percent is due to randomness or other variables. So when you're comparing the two models without the outlier, it makes for a stronger correlation. So the key thing again from this note is the idea of residuals and using residual plots and understanding what residual plots represent and how to read them.